So last day we ended our discussion over here where we have discussed about the linear regression, and we have also seen how to write the code from scratch for the gradient descent part, and also we have seen how we can use the scikit-learn package for implementing the a simple linear regression model for machine learning, right? So one thing I forgot to discuss last day, not to discuss actually, just to inform you that like in linear regression, what basically we have seen that you have only one input variable x and one output variable y. So, but in reality, the output is not always dependent on only one input. Maybe there are multiple inputs responsible, right? So naturally, in that case, if you have say three inputs and one output, x1, x2, x3, and output is y. So, and if you try to draw, the relation between x1, x2, x3 with y, it's not possible to draw, on a 2D plane, right? Because it's a, each and every point, the data point will be represented by three components, one from x1, another from x2, and third one is from x3, and also there will be an output. So it's not possible to draw on a copy. So anyhow, if you have more than one input variable, so in that case what we actually call it for multiple linear regression, something like this. Okay, not a simple linear regression, like where you have a set of inputs and the set of inputs is defined by many dimensions, not a single x, and obviously we have one output which defines definitely a straight line. But if you have a point like this, just assume a scenario. You see, you have two inputs and one output, not three inputs. Why I have taken two inputs and one output? So that we can present on as a three dimension on the on this slide. So we have a lot of points here which is presenting your training data, right? And these points I hope you can easily understand. Say, just assume that they are in a space, a 3D space, where the two dimension is for input and the third dimension is for output. If you want to, you know try to connect all these dots, definitely a straight line cannot do this, because now we are in a plane, not on a not on a 2D dimension, in a 3D dimension. So not I mean we have to draw a plane on this. So you can assume something like we have a plane, a straight plane, which plane is basically, it's exactly the dots are on the surface of the plane, right? So we have to find the equation of this plane, and how we can find the equation. Naturally it will be dependent on more than one variable, so it looks something like this, that y equal to w1 x1 plus w2 x2 plus b, where w1 and w2 are the two weights or some free parameters associated with those two input variables x1 and x2, and b is the bias that already you have seen. And in other words, actually you can represent the same thing in this way. What I have represented here, w transpose multiplied by x plus b. So you can think like this. What this w is, w means w1 and w2, so it looks something like this. So w1 w2, so w transpose means it's a column vector, and x again a column vector, because x means a single point which is combination of multiple, multiple components, like x1 x2 x3 and till xn. Now this value of n will vary, depends upon the data set. For example, in my presence data, the value of n is 2. I have only two components, x1 and x2, which makes a a training data, right? So in this way, actually, we can, the further part is basically same. Just if we have more than one input, then we will go for something like this. Anyway, So we will move further and we will start with logistic regression today. Okay. So anyway, you see from this line, from this name, you can see it's again, maybe you can say that, yeah, this is a regression problem again. But remember, we will actually do a regression, but the usability of this will be for classification. So it's very interesting, you know, because how this regression is used for classification, that's a very interesting thing, I hope. Anyway, so let's move forward and let's see how actually it's happening. To understand the scenario, let's take a problem and try to understand what exactly, you know, a limitation of a linear regression for which we are actually learning this. So just assume a scenario that we have a, say, a input data set, something like this. And it's a very straightforward data set given, just for understanding, which is given that with respect to study hours, I'm just trying to predict whether a particular student have a possibility to fail or pass or not. Okay. Interestingly, in this particular data set, naturally the output is the result and input is the study hours. Where this input study hours, you can say that okay, it's not exactly continuous, but fine. We can have a continuous value. I can say that I have studied 5.4 hours. I can say that. So the input is a continuous variable, but output is not a continuous variable. The output is saying either he will pass or the student will fail. Not in between. I mean, there is no result in between possible. So if we try to, represent this particular data set with respect to a, pictorial view, we can have a diagram something like this, right? Where in the y-axis we are considering the result, okay, and this result will signify definitely in two different category. Either result will be pass or the result will be fail. So we have some data points here and some data points here, which is the part of the training data set, as you can see here. And what it is representing, that these data points are representing the data points for which the student has failed, and these data points are representing some past. And you see in the x-axis it is representing the study hours. So naturally you can easily find a gap between the last data point over here and the first data point over here. So you can have an imaginary line presented here, drawn here, which is basically dividing the uh, points over here. But suppose we have a data set like this and I am trying to solve a problem by linear regression. So what linear regression will try to do, based on the distribution of these dots for pass and fail different data set, the linear regression algorithm will try to draw a line, right? And maybe the line can be something like this, just for assuming you can think in this way, right? Okay, maybe. So in future, how we can utilize this line? We can put, say for example, I have a study hours, say 7.8 study hours. So what will happen for 7.8 hours? What result will happen? So for study hours 7.8, I will just try to project the particular 7.8 dot, that particular dot presented in 7.8 hours with on this line, and then the on the same point which is projected on this line can be projected towards this y-axis as well, right? Now this value of y-axis I will get some value, not definitely fail or pass, some value which is in between 0 and 1 maybe, okay. And if the value is greater than 0.5, then I can say okay, that means the student has passed. And if the result is lesser than 0.5, the student is failed. So obviously this particular solution is not very good, but just for time being, in a very layman term, we can try to find a solution something like this, right? And you see, it's just assume a situation. So this is the 0.5, which is the boundary. Above this is pass and below this is fail, something like that. So if a new data point come, so for some new data point, not, I don't know whether this particular data point will be in this side or this side. I have kept here just to show you in which particular part of the study hours it is presenting. So for some particular value of study hours, we have a point here and we can easily project on this particular line, which will be again projected towards this particular y-axis, and I will get some value. Just what I told you. If this value is greater than 5, 0.5, I will say okay, the student is passed. Fine. And it is true. It should be passed. So naturally this particular point should be in this side. Anyway, I have drawn it here just to show you with respect to study hours how the result is projected through this particular linear regression line. So up to this it's fine. There is no problem. But a problem may occur when we will have a outlier in the dataset. What is outlier? Outlier means you can just assume something like a noise in a signal, like some you are listening some music and some noise is coming, by radio or something like that. So that noise is an unwanted signal, right? And that, in the same way, in machine learning term, for a data set, there may have some data which can be an outlier. For example, study hours, say for example 1.5, and corresponding result definitely should be fail. But suppose in the data set by mistake it is given passed, definitely it is going to be an outlier. In the same way, if we have a data point something like this in this part, just as you can see here, so I have a far apart from here, and because of this particular point came during training, what will happen? The average error will be increased a lot due for this line. So what the linear regression will try to do? Again, this linear regression algorithm will try to minimize this error as much as possible, right? As a result, what will happen? This particular straight line that we had may be diverted towards this side just to manage the error, the least error, right? So maybe the straight line will be something like this, just because of this particular error, to manage this. Because linear regression don't know exactly what you are going to do, what's your plan. So it will do that, but afterwards what will happen? Just you see, we have a point here, some study hours value. Now it's touching in this particular projected line point on this straight line, and as a result I will get a position something like this, which may be less than 0.5, right? And as a result, what will happen? This particular study hours value, the result of this study hours value will be predicted as fail, which is definitely not correct. So there is a very big limitation with respect to this scenario. If we try to apply linear regression, is that it cannot work with outlier. So I have written this one as a gist, that from the case study we have observed that linear regression line is highly influenced by the outlier. The predicted value may exceed range 0 to 1. Yeah, definitely. Because I can have a value something like this here, for example in this point, which will be projected here, which will be greater than 1 somewhere after here. So you cannot do this. Even can be negative is right, this side. So if you point here, it is pointed to a negative, which is again not expected. So your value should be in range 0 to 1. So how to do this? So that means we cannot apply directly linear regression in such classification problems. It's a classification problem. I think it's very clear to you, right? So what to do? Here the logistic regression comes into the scenario. And what exactly this logistic regression is? To understand this, let's start with a very, very basic understanding. Ultimately, what I have a linear regression line presently you have in your hand. But this line is not going to, work much on this particular set of points that you can see here. So what we can apply here, we can actually apply a black box, which is, you can say, a logistic function on the straight line, that is y equal to mx plus c, and as a result we can find a function whose nature will look something like this. So what you can see in this particular diagram, that we have an x-axis, and this axis, say for example z. This x-axis value can be anything. I mean, from minus infinity to plus infinity. This 0, don't think that this is a 0 is x equal to 0. This 0 is written for z value. This 1 is written for the z value. Okay. So value of z is always vary within 0 and 1. But x can be in any side. Towards right it is plus infinity, towards left it is minus infinity. Whatever the value of x in this range, infinite range, always value of z will lie within the range 0 and 1. And that is basically we want. Now, how to do this? The definition of this logistic function looks something like this. Z equals to 1 by 1 plus exponential of minus x. Exponential of minus x means e to the power minus x. Okay. If you apply any value, if you can check in your home that if you apply minus infinity instead of on x, you will find its value 0. If you apply plus infinity on the value of x, you will find the value of 0 will become 1. But it's very close to 1 maybe, but may not be exactly 1, but very close to 1, but it never exceed 1 and never exceed 0 as well. And this will be useful for our case because we can draw a curve something like this, which can easily, it's like a regression, touching all the points in my data set, but it's not a linear regression. We are applying a logistic function over the linear regression equation, and we can do this. Okay. So now naturally question may come that how this logistic function has evolved. Why or how I'm directly saying that z will be equal to 1 by 1 plus e to the power minus x, and how it's working. How? Let's try to understand. Let's try to go a little deeper into this and try to understand what exactly logistic function implies. So just assume a scenario. We have a scenario like this. This particular diagram is very now known to you, and the problem is little bit different here. Not different actually. It's actually thought in a different way. What I'm saying, that consider we have a model with one predictor x, naturally one predictor x, and one Bernoulli response variable y. Why Bernoulli I'm saying? Because it's actually Bernoulli takes a probability whose value ranges between 0 and 1. And what I want this p, and we have a p definitely, which is the probability of y cap will be equal to 1 or not. Y cap means the predicted output. Okay. So definitely we have a linear equation. But assume instead of having y equal to mx plus c, just what we had, or maybe wx plus b, whatever you say, this y, instead of y, I'm trying to find with the probability of this. Okay. So I can write maybe something like this. Instead of y, it's written as p. But this particular equation has a problem. The problem is that we all know that probability ranges between 0 and 1. But this value of WT, normally W transpose X plus B, that means basically MX plus C, whatever you can say, this particular value for some value of X, any value of X actually, can be towards, can be in a range of minus infinity to plus infinity. Because value of X, it's not possible to control the value of X, right? Value of X can be 10, can be 20, can be 1 crore. Even in my, just to check, I can keep value of X minus 1 crore. You can have any range of value in the X. You cannot control that. That's the input. And because of that, if you calculate mx plus c, that particular value can be in range of minus infinity to plus infinity. So if you try to equate these two, it is not possible to equate, because in the left hand side of this equation ranges 0 to 1, right hand side of the equation ranges minus infinity to plus infinity. You definitely cannot equate this, right? Now what is t here? I'm just assuming this w2 x plus b as t. Okay, just assume. That's why I have written t, because of lack of space. So what to do? Here, that means somehow we have to modify this left side part. I mean, I cannot write directly the probability value here. I cannot use this. Instead of what I can do, we can go for a modified version of this one, that is what we call odds of p. Now it's not possible to explain odds of p directly. You can check in internet what exactly odds means. Just for time being, you understand that odds of p means p by 1 minus p. Okay, so if I try to represent the equation of w transpose x plus b with the odds of b, can I correlate? You will see that obviously, right, RHS is always minus infinity to plus infinity, this particular range. So I have to change the range of LHS part to the same, so that I can equate them, right? Now you see, if you put, say for example, say you will see that value of p will, p by 1 minus p will always range between 0 to plus infinity. Why? You see, p by 1 minus p means odds of p, where p is the probability. And we all know that probability value ranges in between 0 to 1. That means maximum value of this p will be 1, minimum value of this p will be 0. Minimum value, if we put minimum value over here, then p by 1 minus p will become 0, right? And if we put uh, uh, maximum value of p over here, then it will become, 1 by 1 minus 1, that means 1 by 0, that means plus infinity, right? So that means odds of p has a range 0 to plus infinity. So the range has been increased, definitely from 0 to 1 it has been increased to 0 to plus infinity, but left side is yet still need to be changed, right? So that means odds of p is not only going to equate with the linear regression equation. Now see what we can do. Just to overcome this scenario, what we can do, we can put a log on this. We can put a log on this odds part. And once we will put log, the equation will now, will have a very interesting change. Why? Because now see, if you put value of minimum value of p here, that means 0. So log 0 will be equal to minus infinity. And if you put p equal to 1, that means this part will become 1. So log infinity will become plus infinity. So you can easily check that in your internet home. So now see, log of odds p is actually in the range of minus infinity to plus infinity. That means if we try to equate the equation of a logistic regression function, that is w transpose x plus b, I have to equate with respect to logs of odds of the probability. That this is what, right? Now we can proceed. So proceed means what? ultimately what we have to find out? We have to find out with respect to probability, value of p. What is the equation for this p we have to find out, right? So I have got this equation where I can equate these two. They are in the same range. Now here I have to, nullify this log, as well as I have to find out what will be the value of p. So what is the simplest way? The simplest way is that apply exponential in something like this. We all know that we can simply apply e to the power LHS equal to e to the power RHS, because now LHS equal to RHS I can say based on their range, right? So if I have a something like this, and we all know this log is based on base, I mean it's actually the base of log is e. So naturally e to the power log of p by 1 minus p, it means basically p by 1 minus p, log will cancelled, right? And I will have in the right hand side I will have e to the power wtx plus b, right? So equation become much more easier for me right now. Now let's do one thing. Let's take a assumption just to simplify the solving process. The assumption I have taken that e to the power w transpose x plus b as y. Okay, that means p by 1 minus p is equal to capital Y. Okay, and from here we have to find out the value of p. Okay, and I think it's very easy right now. Okay, so p will be equal to 1 by, I mean y by 1 plus y. Naturally, here if you just I have a step jump here, you can check in your home, and then I can simply write y by 1 plus y means instead of y, if I put this value e to the power w transpose x plus b by 1 plus e to the power w transpose x plus b, right? Interestingly, you see this is exactly, now question is that what we can do here, we can divide the numerator and denominator both by e to the power w transpose x plus b. If we do that, what will happen? The numerator will become 1 and the denominator will become 1 by e to the power w transpose x plus b plus e to the power minus just a minute, I have a mistake. The numerator will become 1 and the denominator will be yes, denominator will be 1 plus e to the power minus w transpose x plus b, something like this. Okay, again I have a step jump here, just for shortage of time I have done that, but what you can do in your home, you can try just divide this numerator and denominator both by this e to the power w transpose x plus b and check it. You will find this equation. And if you can recall what exactly we have seen in the logistic function in my previous slide, I think you can recall that it was z equal to 1 by 1 plus e to the power minus x, right? So instead of having minus x, have here w transpose x plus b. So it's basically having a similar equation, similar type of equation, right? Now I hope now you can understand that why exactly I arrived that logistic function term in my previous slide. And that is the reason why we have this logistic function. I mean this particular type of function used in logistic regression. Okay. So now what we can do, and especially there is a very interesting thing over here. This particular type of function we call sigmoid function. Okay, and there is an enormous importance of this sigmoid function throughout your machine learning journey from today. Okay, in future you will see that this particular sigmoid function will become extremely vital for learning lot of different complex models in future. Okay. So now let's what we can do. We can try to investigate that why this sigmoid is so important and why why the people give so much importance on this sigmoid function. Sigmoid function means a function having this type of signature 1 by 1 plus e to the power minus x. I mean instead of x it can be y, can be z, can be anything, but in the form of like this. Okay. So now let's do one thing. Let's try to check why we give so much importance on this sigmoid function.